Hello and welcome to the Complete Paper 2 revision lesson. You wanted one, you begged me for it, and now you're going to get it. We'll start with algorithms and computational thinking. Computational thinking is all about structuring solutions to problems in a way that computers can easily follow. The key parts of this are decomposition, abstraction, pattern recognition, and algorithmic thinking. Decomposition is breaking a problem down into smaller subproblems. Once each subproblem is small and simple enough, it can be tackled individually. Abstraction: removing or hiding unnecessary details from a problem so that the important details can be focused on or more easily understood. Pattern recognition: looking for similarities amongst and within problems. Algorithmic thinking: deciding on the order that instructions are carried out and identifying decisions that need to be made by the computer. 2.1.2 Designing, creating, and refining algorithms. Computer systems accept input from a user, or from sensors, or from a data file. They process that data. They output that result back to the user in some format. Programmers write programs to process inputs in order to provide the needed output. A structure diagram is a graphical method of decomposing a problem, with each layer breaking down the layer above it into smaller and smaller subproblems. So let's imagine I want an S1 Perry merch system so people can go online and buy their t-shirts and hats and caps and mugs and everything else. I decompose this merchandise system into 4 sections: a user login, a search, a sales, and a reorder function. I could then break down, for example, the sales section into a shopping basket and a payment. Flowcharts. A flowchart is a graphical representation of an algorithm and uses symbols to denote each step, with arrows showing how to move between each step. We have a line, which is an arrow representing control passing between the connected shapes. We have the rectangle, which is a process. This shape represents something being performed or done. We have the subroutine, and this represents a subprogram like a function or procedure that will relate to a separate non-linked flowchart. We've got the kind of parallelogram, the rhombus-shaped input or output. This shape represents the input or output of something into or out of our flowchart. We've got the diamond decision. This shape represents a decision which could be yes or no or true or false. That results in two lines only, representing the different possible outcomes. And we've got kind of the rounded rectangle, which is our terminal, and this is for a start or an end of the process. Here's an example flowchart representing a program that repeatedly asks the user to enter a number and then adds this to the total. When the user elects not to continue, it'll print out the final total and then end the program. So we start with a start, and then we have a process where we set the total to 0. We then have a input because we're asking the user to enter a number. We have another process where we do a little bit of maths. And then we have a decision. Would the user like to enter more numbers? If the answer is yes, we loop back and we enter the numbers and do a bit more math. If the answer is no, we output whatever the total is, and then we end the program. Pseudocode is a textual representation of an algorithm. It is very closely related to high-level languages. In fact, it's kind of a general mix of all of them, although it does not require the same precise use of syntax. Remember, there is no such thing as correct pseudocode. Pseudocode enables programmers to communicate algorithms to other programmers without having to worry about which language they all know. Here's an algorithm that finds out whether a positive number is odd or even through repeated subtraction. Input number while number greater than or equal to 0. If number equals 1, then print odd. Else if number equals 0, print even. End if. Subtract 2 from the number, store it as number again. End while. If you've studied any kind of language, Java, C#, Python, doesn't matter, you can understand this program. Okay, it's not specific to any one programming language in terms of syntax, it's just generally understandable by any coder. Please note though, even though the syntax is loose, you must still use coding keywords and structure it like a program. If you're giving an answer in pseudocode, it's not just explaining it in English, okay? You've got to use those keywords. You've got to use a programming type structure. That brings us on to the OCR reference language. For the J277 exam, Paper 2 Part B, you will be asked to answer questions in either the OCR reference language or a high-level programming language of your choice. OCR reference language is not really pseudocode. It's kind of a strictly formalized version of pseudocode with a precise syntax that you need to follow or you will lose marks. By high-level language, it means any of the languages that you will probably have studied as part of your course. So Python, C#, C++, C, Java, JavaScript, etc., etc. Trace tables and identifying common errors. When an algorithm has been defined, it needs to be checked for correctness. A trace table is a tool that can be used to follow each line of an algorithm through step by step. The trace table will show the contents of each variable after each line has been carried out, and will also show any output. By having a trace table and running through it, you can identify errors quickly and effectively. So let's have a look at a very simple program here and the trace table that comes from it. Program's very simple. Number equals 2, while number less than 11, print the number, add 2 to the number. Pretty simple. But if you have a look at the trace table here, it seems quite large because you'll think, well, this is only 4 lines of code. Why do we have so many lines? Well, to create a trace table, we first of all write down all the lines that are going to be executed. Then we write down all the variables, all the outputs, all the conditions that need to be checked. And we end up with something like this. So we're going to start with line 1. Our variable is number, and we set that initially to 2, don't we? Then we move on to line 2. What do we do in line 2? Well, we say while number less than 11. Well, the number is currently 2. Is 2 less than 11? Yep, that is true. We move on to line 3, which is printing the number. That means we're going to output the value of number, which is 2. We then move on to line 4. Line 4, we're adding 2 to the number and storing it back as number, so we now have a value of 4 for number. Now here we go back to line 2, because it's a while loop. We jump all the way back to line 2 until while number is less than 11. So we go back to line 2. Is 4 less than 11? Yep, that's true. And we continue on down our program. Eventually, we're going to say, oh, add 2 to number, and we get 12. Then we jump back to line 2, and we're going to say, is 12 less than 11? Actually, that's false, and we're going to exit that loop and continue with the rest of the program. In the case of this program, it'll finish. This is quite a complicated example, but just to show you how to create a trace table that you might have to do in your exam. Please note, although some exam questions will ask you to fill in a trace table, sometimes you might want to do a trace table for programs anyway. So for example, if you're given some code and asked to find a logic error, and you can't find it straight away, do a quick trace table, run through it, and you should find the error quite quickly. Oh, this is a good one. Searching and sorting algorithms. Starting with standard searching algorithms. A linear search is carried out by inspecting each item of the list in turn to check if it is the desired value. If it matches, you have found the item. Otherwise, the next item in the list must be checked. If the algorithm gets to the end of the list without finding the item, then it is not in the list. The linear search is relatively inefficient, but it works on any list even if the data is not sorted. It's also pretty easy to code. Every single item in the list must be checked before you can be certain that the item required is not in the list. If we have a look at the algorithm in pseudocode, it looks something like this. Repeat until number is found or the end of the list is reached. Check one value from the start. If the value matches what is being searched for, output the value, stop. Else, if the end of the list is reached, output not found and stop. End if, move to next value. If we have the following list, let's have a look at an example finding 9 in this list using a linear search. We look at the first item in the list. It's a 7. 7 is not equal to 9, so we move on to the next item in the list. 2 is not equal to 9, so we move on to the next item in the list. 9 is equal to 9. We found a match, we can stop checking. If we got to the end of the list and we still hadn't found 9, we could be certain that 9 wouldn't have been in the list. A binary search is a much more efficient algorithm to find values in a list. However, for a binary search to work, the list must be in order. The middle value in the sorted list is picked. If there is an even number of values and there isn't an exact middle value, generally the value to the left of the middle is chosen. If the middle value is the one you're searching for, then the algorithm finishes. However, if not, you can discard the bottom half of the list if the middle value is smaller than the one we were searching for, or discard the top half of the list if the middle number is larger. Either way, we always also discard that middle value. And that's in bold because that's a mistake I find students often make. They forget to discard that middle value, and that can ruin the rest of their explanation in an exam question. You then repeat the process by choosing the middle value of the remaining items and comparing this to the value required. If you get to a situation where the list only has one item and it's not the one we're searching for, then the value is not in the list. A binary search is very efficient. You can find a specific value in a list of 1 million numbers in a maximum of 21 comparisons. Whereas with a linear, you might have to make 1 million comparisons if it was the final number. But remember, it only works on a sorted list. The algorithm in pseudocode would look a bit like this. Repeat until value found, or list is of size 1 and the value is not found. Pick the middle value in a list. If the value matches what is being searched for, output the value and stop. Else if the value searched for is greater than the middle value, discard the middle value and the bottom half of the list. Else if the value searched for is less than the middle value, discard the middle value and the top half of the list. End if. Again, let's have a look at a worked example. So we've got a list of items here, and we'd like to find 2 using a binary search. Note, the list is in ascending order. So first of all, we find the middle value, which in this case is 4. So 2 doesn't equal 4. 2 is in fact less than 4. So therefore we discard the middle value, which is 4, and the entire top half of the list. And that leaves us with just 1, 2, and 3. We repeat the process, we find the middle value, which is 2. 2 is equal to 2 in this case, so we have a match and we can stop checking. Moving on to standard sorting algorithms. The bubble sort algorithm works by comparing pairs of values. If the 2 values are in the wrong order, they're swapped over. This is then repeated for each further pair of values. When the last pair of values has been compared, the first pass of the bubble sort algorithm is complete. The algorithm will repeat until a pass has been completed with no swaps occurring. Once this happens, we know the list is guaranteed to now be in order. Again, here's an algorithm in pseudocode. Repeat until no swaps are made. Repeat for each pair in the list. If the list item x is greater than the list item x plus 1, then we swap the values, and that's it. Nice and simple, we hope. So again, here's a worked example. We've got 6194 in our list. We want to get this in ascending order. So we're going to start by comparing 6 and 1. They're in the wrong order, so they're swapped over. Now 6 and 9 are compared. They're in the correct order, so no swap is needed. Next, 9 and 4 are compared. They're in the wrong order, so they're swapped over. The first pass is now completed. We have 1, 6, 4, 9 in our list. Since at least one swap has taken place, we need to repeat the algorithm. 1 and 6 are compared. They're in the correct order, so no swap is needed. Now we compare 6 and 4. They're in the wrong order, so we swap them over. Next, 6 and 9 are compared. They're in the correct order, so no swap is needed. We're left with 1, 4, 6, and 9. Although I can look at that and go, yes, it's in the correct order, because a swap did take place in the last pass, the algorithm has to repeat, even though the list now does appear to be in numerical order. So we do another pass, we compare 1 and 4, 4 and 6, 6 and 9. No swaps will take place, and because no swaps have been carried out, we know the algorithm is complete and the values must be in order. The insertion sort algorithm splits the list to be sorted into 2 parts, a sorted side and an unsorted side. Initially, the sorted side contains just the first item in a list, with everything else on the unsorted side. Unlike a bubble sort, an insertion sort does not require multiple passes to check that the values are in order. Once each value has been inserted into the sorted list and the unsorted list is empty, the list as a whole will be in order. Insertion sort is more efficient than the bubble sort algorithm, but can be relatively tricky to implement in a high-level language. Moving values around without overwriting other values can be difficult for inexperienced programmers. If we have a look at the pseudocode, it looks easy. Split the list into a sorted section containing the first item and an unsorted section containing the rest of the values. Repeat for each item in the unsorted section. Insert each item in turn into the sorted section, placing it in the correct place. Superficially, looks very easy. Trying to implement this in, say, Python or C# or something is a lot of coding, trust me. So again, here's a worked example. We start with a sorted list containing just the first item, which is 6, and we have the other items in the unsorted list. We take the first item from the unsorted list, which is a 1, and we insert it in the correct place in the sorted list, which is before the value 6. We repeat this for the next item in the unsorted list. 9 is inserted into the sorted list after the 6. Now the final item from the unsorted list, 4, is taken and added into the correct place in the sorted list, and we have 1, 4, 6, 9. At this point, all the numbers have been inserted, and the list can be said to be in the correct order. The merge sort algorithm uses a divide and conquer approach to split data up into individual lists and then merge these back together in order. The way that the lists are merged back together is a key to understanding how this algorithm works. The merge sort is much more efficient than either a bubble or an insertion sort. It will sort a large list of random values in a quicker time. However, a merge sort may not be the best sorting method for nearly sorted or small lists. Again, here's a quick look at some pseudocode for this. Repeat until all the lists are merged. Repeat for each pair of lists. Repeat until all the numbers in pairs of lists are merged. Compare the first value in both lists. Insert the larger of two values into a new merged list. Remove value from the old list. So again, here is our list 6194. Here's a worked example to sort it in ascending order. First, in the divide stage, the original list is split into two sublists, 61 and 94. Each of these is now split into two sublists, so each contains only one element. So basically, we split everything off, and so it's just one number in each sublist. So we have 6, 1, 9, and 4. Then each pair of lists are merged together in the conquer stage. Where there is an uneven number of lists, the odd list will simply remain unmerged until the next step in the process. So let's have a look at what we do. 6 and 1 are compared, with 1 being inserted into a new list before the 6. In the same way, 4 is inserted before 9 in the next merged list. So we have two sublists now, 1, 6, 4, and 9. This merging process is then repeated to merge the pairs of lists together. 1 and 4 are compared to decide which value will be first, with 1 being inserted. 6 and 4 are then compared, with 4 being inserted. 6 and 9 are then compared, with 6 being inserted before 9 is finally inserted, and we end up with a list in order of 1, 4, 6, 9. Now we're going to look at programming fundamentals, starting with some of the fundamental aspects of programming that we need to know about. A variable is a name or a label or an identifier which is used to identify a memory location to store a value that can change while the program is running. A constant is a name or a label or an identifier which is used to identify a memory location used to store a value that cannot change while the program is running. Please do not say a constant is like a variable but it can change. That will not get you any marks in the exam. Make sure you learn those definitions. They come up a lot in exam papers. Both variables and constants are assigned using the equal symbol. So the variable age equals 12. The value 12 gets stored as age. I can say const for constant pi equals 3.14. So in that memory location labeled pi, we now have the value 3.14, and it cannot be changed elsewhere in the program. Data can be input from the user and output back to the user while the program is running. So input is usually something like this. Number equals input, enter a number. To output, we usually just use the command word print, as in print number. So input and print are your keywords to take away for inputting data or outputting data from a program. Moving on, let's have a look at the three basic programming constructs used to control the flow of a program. They are sequence, selection, and iteration. Sequence is the execution of statements one after the other in order. Programs run from top to bottom. Selection is the construct used to make decisions in a program based on the result of a Boolean condition. If we have a look here, we've got some examples both in the OCR reference language and in Python. Starting first with the OCR reference language, the classic method of doing selection is the if, else, if, else. So let's have a look at this program. If value greater than 50, then print number over 50. Else if value greater than or equal to 20, then print number is 20 or over. Else print under 20, end if. We can replicate this program in Python as follows. Almost exactly the same code. We don't need the then. We use elif instead of else if. And we don't need to worry about the end if at the end, as long as we've got our indentation correct. So Python, very similar to the OCR reference language here. You can use either, of course. However, the OCR reference language has another form of selection that isn't available in Python, and that is the switch case or select case code. If you have a look at this example in the middle, switch name, case equals Bob, print hi Bob, case equals Tom, print howdy Tom, default, print I don't know you, end switch. If you're used to Python, or another language that doesn't have a switch case statement, this might look a little bit strange, but in fact it's very easy to replicate as an if, else, if, else. So if I were going to create this in Python, I would just recreate it as follows. If name equals Bob, print hi Bob. Elif case equals Tom, print howdy Tom. Else print I don't know you. So you can see converting between a switch case and an if else is very simple. In the exam, you won't be expected to write a switch case like this. However, you might get code that is a switch case that you have to understand and answer questions about. The final programming construct is iteration. Iteration is the construct used to repeat sections of code, often called looping. There are two different types of iteration that you need to know: count-controlled iteration and condition-controlled iteration. Starting with count-controlled. This repeats the code a defined number of times. This will always use a for loop. Here are two examples, one in OCR reference language, one in Python. Both of these will print the same. They will output 1, 3, 5, 7, and 9. In OCR reference language, we would do this as for count equals 1 to 10, step 2, print count, next count. We start at 1, we keep going until we get to 10, and we're doing this in steps of 2. So 1, 3, 5, 7, 9. You can omit the step section if you're just going up one at a time. You don't have to say step 1. You could just say for count equals 1 to 10. In Python, very slightly different. We say for count in range, 1, 11, 2, print count. Python, the first number here is the start value, and that's inclusive. So it starts and includes 1. The second number, however, is exclusive. It's 1 more than you need. So while in OCR reference language we say 1 to 10, in Python we say 1, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then stop. The first number is inclusive, the final number is exclusive. And then we're doing this in steps of 2. So again, if you're doing this in steps of 1, you can miss this out. You could just say 1, 10, but because we want to do it in steps of 2, we have to include this final stage. The next form of iteration is condition-controlled iteration. This checks the condition each time around the loop and decides whether to repeat the code again or continue the rest of the program. This can use the while or do until structures. Starting with the while structure, the OCR reference language and the Python version of this are both very similar. Starting with the OCR reference language, we could have an example like this. Continue equals y. While continue is equal to y, continue equals input continue, end while. And this will keep repeating the question continue until you type in something other than a capital Y. The Python over here is very similar, except we are omitting the end while because we don't need that. In the middle here, we have the do until structure. This is a structure that exists in the OCR reference language, but does not exist in Python. The main difference here is that it's a post check, in that it checks at the end of the block of code, rather than a pre-check, like a while loop, that checks the condition at the start of the block of code. So we have do continue equals input continue until continue is equal to Y. This will always execute at least once, whereas a while loop might never execute if that condition is not true. Arithmetic operators are used to carry out basic mathematical operations on numerical values, or numbers to you and me. Most of these are very similar in the OCR reference language or in Python. We use the plus sign to do addition, minus sign to do subtraction, multiplication uses an asterisk, and division uses a slash. Please, please, please make sure you use those in your exams. Don't use an X for multiplication, that's a very common mistake. Use an asterisk, that's how we do multiplication. An X is a variable. If you put 4x5 in your program, that will crash it because it'll think X is a variable. In the same way, we don't use a classic division symbol, we use a slash because that's just what we use when we use a programming language. Now we have the mod operator, which is a percentage sign in Python. This is modulus. It returns the remainder after a division. 10 mod 4 is 2, because when we divide 10 by 4, we have a remainder of 2. And then we have div, or a double slash. This is floor division, or quotient, or integer division, however you want to call it. This returns a whole number after division. Basically, it tells you how many times one number fits into another. 10 div 3 equals 3, because 3 goes into 10 3 times. Then we have the little hat symbol, or a double asterisk, and this is the exponent operator. Basically allows you to put one number to the power of another number. So 2 exponent 4 equals 16, which is the same obviously as 2 to the power of 4, or 2 times 2 times 2 times 2. Comparison operators are used to evaluate expressions to a Boolean true or false condition. The double equals means equals to. We have not equal to, less than or greater than, greater than or equal to. Again, make sure you memorize these. It's very easy to get them mixed up in an exam. If you get the greater than or the less than symbol the wrong way around, you're not going to get any credit for your answer. In the same way, it's less than symbol, then equal to, greater than symbol, equal to, not the other way around. Don't make silly mistakes that could cost you grades in the test. Boolean operators can allow multiple conditions to be evaluated. So we've got AND, which means it requires both conditions to be true. So a simple example here would be, if username is equal to S1Perry and password equals 12345, you can log into my system. Or requires one or the other or both conditions to be true. So while continue equals capital Y or continue equals lowercase y. Both of these will let the code execute. And not reverses the true or false outcome from a condition. So here, if not number mod 2 equals 0, print odd. I could change this and say, if number mod 2 not equal to 0. This would also give you the same result. Moving on, let's look at data types and casting. Integers are whole numbers, either positive or negative, that have no decimal or fractional part. So for example, 8 or minus 17 for example. Real numbers are used for positive or negative numbers that have or may have a decimal or a fractional part. So minus 8.5 is a real number. 17.0 is a real number. Still has a fractional part. Boolean variables only ever store true or false. A character is a single item from a character set. For example, the capital A or the ampersand symbol. A string data type is a collection of characters that can be made up of letters, numbers, and or symbols. So for example, hello world exclamation mark is a string. Casting is the conversion of one data type to another. The casting functions in both the OCR reference language and Python are very similar. So we have the str function, which in both OCR and Python will convert usually a number to a string. Why would we want to do that? Well, it's usually when we want to concatenate, to join two strings together, like in this example. We want to take the number and join that to the string answer equals, so we need to change the number from, say, an integer or a real into a string before we can do that joining, and then we can print it. Int is a very commonly used one, and that will convert a string typically into an integer, so that we can do math with it. The OCR reference language has real to convert a value into a real, whereas Python uses float to do the same thing. Again, you might have a string that somebody's entered, and you need to convert it into a number that may or will have a decimal place or fraction, so we can use real to do that. And then we've got bool, which is used to convert something to a boolean. I'm not sure when you would ever need to do that in any of your programs, to be honest. The example here from the OCR is bool true to convert the string true into a boolean true. Doesn't work the same in Python. In Python, the bool function would just return true if there is a value and false if there is no value. So it works slightly different in Python. As I said, I'm not sure you'd ever have to use that, but it is in the spec, so I'm including it here. Moving on to the good stuff, let's look at the additional programming techniques. This is all the nice complicated stuff. String manipulation allows strings to be sliced, concatenated, or modified. Slicing means to extract or slice individual characters from a string. Concatenation means to join strings together. I love that word, concatenation. It's just one of my favorites. Okay, this slide looks quite complicated because I've tried to pack in as much information as I can. If we start with a variable that I've called phrase that contains the string computer science, let's have a look at some of the different functions that we can call to manipulate this piece of text. So in the OCR reference language, we can use .length. In Python, we can use len to count the number of characters in a string. So phrase.length or len phrase will return the value 15 because there are 15 individual characters in that string. From 0 to 14, including the space, that is a character, we have 15 characters. To extract characters from the string, in the OCR reference language, we can use .substring with x and y coordinates and brackets, and in Python we can use square brackets x:y to do something similar. With the OCR version, x is the starting position. Remember to start counting from 0, of course, of the slice, and y is the number of characters that you want to take. So phrase.substring 35 would return pewter. Why? Well, we start at position 3. And 3 would give you P. We're then taking 5 characters. So 1, 2, 3, 4, 5, and that would then give you pewter. However, the Python version works slightly differently. With Python slicing, x is the starting position of the slice, and y is the finishing position plus 1. Because it's Python, the second number is always exclusive, not inclusive. So if I wanted to get pewter from the phrase computer science, I would need to say phrase, square brackets, 3:8. So why? Again, I want to start with position 3, and I want to go until I get to position 8, but actually 1 before. So 3:8 would give me PUTER. So phrase.substring 3,5, start at position 3, take 5 characters. Phrase 3:8, start at position 3, inclusive, keep going until you get to character position 8, exclusive, so stop at 7. In addition to this, if you are slicing up strings, the OCR reference language also offers .left and .right, where you can give a certain number of characters you want to slice from the left or from the right. So phrase.left4 would give you the first 4 characters, comp. Phrase.right3 would return the final 3 characters, NCE. There's not really a .left or .right equivalent in Python. You can still slice that way if you want. If I said phrase:4, that would give me comp. If I said phrase -3 colon, that would give me NCE. But again, you probably won't have to do anything that complicated. Both the OCR reference language and Python have the .upper and .lower functions. The difference is with Python, you just have to have that open close brackets at the end because it's a function call. But obviously, .upper will convert a string to uppercase, .lower will convert a string to lowercase. Nice and easy. We can also concatenate or join the strings together using plus. Nice and simple. And we've also got the ability to convert characters to ASCII values and ASCII values to characters. In the OCR reference language, we use ASC, whereas in Python, we use the ORD function. This will find the ASCII value of a character. So ASC capital A or ORD capital A will give us 65. The reverse is using the CHR function, uppercase for OCR, lowercase for Python, but CHR 65 will return back the capital letter A. The use of basic file handling operations. Files can be read from and written to by a program. Files must be opened before use. Files must be closed once operations are completed. Very important. Opening and closing is usually 1 mark each. You must be able to read a line from a file. You must be able to write a line to the end of a file. And you must be able to iterate through a file. Starting with reading from a text file. Imagine we had a problem like write a program to read all the data from the text file data.txt and display each line on screen. How would we go about doing that? Well, in the OCR reference language, we would start by saying something like data file equals open data.txt, using the open command to open the text file that we've been given. Then we would say while not datafile.endOfFile, using the endOfFile command to tell the program when we reach the end of the file. We would then say line equals datafile.readLine. ReadLine reads the next line from the text file. We print that line, end the while loop, and then close the data file using the close command. In Python, it's probably a little bit easier. Data file equals open data.txt R for read mode. For line in data file just loops through each line in the data file. We print that line and then we remember to close the data file. Now let's take a look at writing to a text file. The problem this time is to write a program to repeatedly ask the user for a name and save that name to the text file data.txt until the user types in end to quit this section of the program. Starting again with the OCR reference language, we open the data file. We set the data to a blank string. While the data is not equal to end, we ask the user to input the name. If the data they've typed in is not equal to end, as in they don't want to finish that program, then we take that item of data and we write it to data file using the writeLine command. We then end the if, end the while, and make sure we remember to close the data file. Again, Python is very, very similar here. The only real difference is that when we open a file in Python, we have to specify the mode. So here we're going to use W for write mode. And instead of using writeLine, the command in Python is write to write a line of data to a text file. Again, please remember datafile.close at the end, otherwise you might lose a mark in the test. Moving on to the use of records to store data. A record is a data structure that allows multiple data items to be stored, using field names to identify each item of data. To create a record, we must first define the field names that will make up each record. We can then store data under these field names in a database management system, DBMS, using a table. So you have a look here, we have a table called address book. It contains the fields first name, last name, telephone, and email, and there are 4 records in that table. SQL, or Structured Query Language, is a database language used to access data stored in a database. There are 3 main keywords that you need to be aware of for the GCSE syllabus. Select from where. Select identifies the fields to return from the database. Basically the columns. From identifies which table the data will be returned from. And where allows the programmer to include search criteria with only the matching records being returned. Where is actually optional. All SQL queries are going to have select and from, and sometimes we'll have that where as well, but you don't necessarily need it. So an example would be, I would like to display the first name and the email address from the table address book of everybody who has the last name Mills. So I would say select first name, comma, email from address book where last name equals Mills. Note that Mills is in speech marks here, inverted commas, because it's text. If it was a number, I wouldn't need that, but it's text, so I still need to put speech marks around it, just like I would if I was writing in Python or another programming language. And when I run this, it will return Graham and GW at notexist.cot. Again, it's only giving me the first name and email from this table where the last name equals Mills. So if you look at that table, you can see that quite clearly. To show all the fields in a table, you can also use the asterisk symbol. So if I just want to return all the fields from every record, I could say select star from address book. Don't need the where clause here, there's no criteria. And this is the same as saying select first name, comma last name, comma telephone, comma email from address book. I can just say select star to mean every field. Moving on to another fan favorite, we have arrays, including both 1D and 2D arrays. A one-dimensional 1D array allows a programmer to store multiple items of data under a single identifier. Each item is accessed through a single index number. A two-dimensional or 2D array allows a programmer to store multiple items of data under a single identifier in a table structure and access each individual element using a combination of two index numbers. Unless you're told otherwise in the question, assume that arrays are zero indexed. The first item in the array is position 0. But never trust the exam board, always double check, they'll give you an example. Is that first value a 0 or a 1? Because that will change a lot of your answers. Also, please remember, traditional arrays can only hold a single data type. For example, all the values are integers or all the values are strings. If you are a Python programmer, Python doesn't actually use traditional arrays. It uses lists, which are more advanced. And lists, you can mix up different data types, it's not a problem. But in the exam, everything's a traditional array. You're not going to mix and match data types in the array. So let's imagine we've got a simple array of colors, red, green, blue, pink, and yellow, and the name, the identifier for this array is colors. So in the exam, they're not going to give you these lovely index values on the top. All right, if you see a list like this, the array, always write on the values, right? 0, 1, 2, 3, 4, or whatever above it. Otherwise, you will make mistakes when you're programming it, okay? It's very easy to make a mistake. OCR and Python, both very, very similar in how you would deal with a one-dimensional array. Colors square brackets 2 would return the third item from your array, which is blue. So 0, 1, 2, third item is blue. If I want to put a value into my array or replace a value in my array, I can do it like this. I can say colors square brackets 1 equals purple. That goes to colors position 1 and puts in the value purple. Since the value green is already there, green would get replaced by purple. Note, and this is really important, you will not be asked to create and initialize the array in an exam question. You can assume that somebody has already created that array. You can just refer to it by the name given to you in the question, okay? Don't waste your time actually creating this array colors. It's just wasting time in the exam that you could be spending with other more important questions. Two-dimensional arrays give you a table structure. You get columns and rows. So again, it'll just give you the array. It won't give you the index value, so write those above it. Write down the numbers of the columns, write down the numbers of the rows so you don't make a mistake. With two-dimensional arrays, please read the question carefully. When it comes to the index values, is it row and then column or column and then row? There will always be an example in the question to make this clear. So for example, for this two-dimensional array, the question might say that 0, 1 returns purple. So you can have a look at this and go, okay, 0, 1, purple, purple, purple. Okay, here's purple, and we've got the 0 here, and we've got the 1 here. So obviously, the column is 0 and the row is 1, so it's column and then row. Okay, I know that for all the rest of the questions in this sequence. OCR and Python, very similar to how we refer to two-dimensional lists, just a slight difference here in how we refer to the index positions. So if I want to return the item salmon in OCR reference language, I say colors, which would be the name of the array, square brackets 1, 2. So that would be column 1, row 2, which would give you salmon. In Python, we don't have the comma, we just have two sets of square brackets. So I'd say square brackets 1, square brackets 2 to return the item salmon. So again, 1, 2, that gives me salmon. Again, to add or replace values, very similar, just have to make sure you phrase it correctly if you're doing the OCR reference language or Python, but colors 3, 1 equals purple would replace white with purple. So again, that would be column 3 in this example. And then we would go down to make sure we are at row 1. So column 3, row 1, replace white with purple. Now we're getting to the complicated nitty-gritty. In exam questions, you will often be asked to iterate or loop through arrays to do something like work out the sum, or work out the average of a set of numbers, or print all the values out, or reset all the values to a blank value or to 0 or something like that. This is one that throws a lot of students, but you just have to be able to use a for loop. So imagine here I've got an array called numbers, 3, 2, 4, 3, 3, and the exam question tells me I have to calculate the total and output the result. I'm doing something multiple times, so I'm going to have to iterate. I'm going to have to use a for loop. It's got to be a for loop because it's going to be done a definite number of times, so it's going to be a count-controlled loop. How do I do that in the OCR reference language? Well, I start by saying total equals 0. Then I need to loop through all the elements, all the items in my array. So again, we think about that. And we think, right, I need to write down those index values. So that's a 0, that's a 1, that's a 2, that's a 3, that's a 4. Because otherwise I will make mistakes in the exam. So I need to go for x equals 0 to 4. Then I say total plus equals numbers x. This is the bit that people often make out. Whatever your loop counter is, counter loop x, y, I, j, whatever, that is what you're going to use here. So it's the name of the array plus the loop counter, and that means you'll transfer each value into total. Next x, because that's just how you do it in OCR reference language, and then outside of the loop, I print the total. Python is very similar. Initialize the value of total, total equals 0. For x in range 0, 5, again, be careful here. 0 is the first value. The second value is exclusive, so it's one more than we need. So if we want to go 0, 1, 2, 3, 4, we say 0, 5. Again, we add whatever was in that position of the array into total, and then we print it out. And that could be worth 4, 5, even 6 marks in an exam. Often just that second line, that for loop line, could be worth 3 marks. 1 mark for using a for loop. 1 mark for having the correct start value, 1 mark for having the correct end value. 3 marks for 1 line. So study these examples, decide if you're going to use the OCR reference language, you're going to use Python, make sure you memorize a few examples. This sort of looping through the array and working out a total or working out an average or something like that come up a lot, especially with one-dimensional lists. If you're really unlucky, in the exam you might get a two-dimensional array question. These very rarely come up, but you never know, they might do. If you get a two-dimensional array question, you will have to loop through the columns and then the rows, or the rows and then the columns, depending on the question, in a set of nested for loops. Again, read the question carefully. In this question, it tells us that colors 1, 0 is green. So that must mean we're dealing with a column first and then row numbering system. But again, make sure you write those numbers on there. Column 0, column 1, column 2, column 3, column 4. row 0, row 1, row 2. Write them down, otherwise you will make mistakes. In the OCR reference language, we're going to have nested for loops like this. Go through all the columns. 4x equals 0 to 4. Go through all the rows. 4y equals 0 to 2. Again, from that diagram I've written down the values, you can see we've got 5 columns, so 0, 1, 2, 3, 4. We've got 3 rows, 0, 1, 2. Make sure they're indented properly, and then I could say colors x comma y equals open close brackets, because this particular exam question I haven't mentioned, but you can probably read it, just says reset each color in the array to an empty string. So I just say colors xy equals blank string, next y, next x, and that will run and reset and take away all the colors and replace it with empty strings. In Python, again, I have to remember that the second number is always going to be exclusive. So first of all, I'm going to loop through the columns and say 4x in range 0, 5, again adding 1 more than I need. 4y in range 0, 3, adding 1 more than I need to the rows. And then colors xy, separate sets of square brackets, equals open close string. You might have read this in the slide already, but I'm going to go through it. Please note you will be not asked to create the array. The arrays are created already. So many people will get that kind of exam question and they'll spend 5 minutes creating the array in Python or OCR reference language, writing out red and green and blue and pink and yellow and purple. No, don't do it. You just have to manipulate it. It already exists. You can assume colors has been initialized correctly. You just have to use it in your code. Subprograms. We love subprograms. Subprograms are programs split into multiple sections. This makes the code easier to read and maintain, reduces the size of the code, and promotes code reuse without copying and pasting. There are 2 types of subprogram, procedures and functions. Procedures are a subprogram that does not return a value to the main program. Functions are a subprogram that does return a value to the main program. Functions, the keyword return must be used when defining the function. So a procedure doesn't return anything, a function does. That's the main difference. So let's have a look at procedures and functions in both the OCR reference language and Python. In the OCR reference language, we start a procedure with the keyword procedure, then we give it a name, check the exam question in case there's a name already used that you have to use, and then in brackets, any of the parameters. Parameters are values that will be passed to the procedure to be used inside it. In this case, we have 2 parameters that I'm going to call num1 and num2. Then inside my procedure, I'm going to do something. In this case, I'm going to add number 1 and number 2 together as total and print it out. And then I'm going to have the end procedure keyword. Python, we don't need to say procedure. For all subprograms, subroutines, we always start with the keyword def, then the name of the subroutine, then the parameters, do something with them, print them out, for example. I don't need to worry about ending the procedure. Python does that automatically. With functions in the OCR reference language, we use the keyword function. Again, we have the name of the function, any parameters, we do something, and then we've got this key here. We've got the return. We're returning the value of total back to the main program. Don't forget the return when you're writing a function. And then OCR reference language, we finish with end function. Python, we don't have to distinguish between procedures and functions in the header. We just say def addition, num1, num2, add number 1 and 2 together as total, but we must have return total. That's how we know whether we're dealing with a Python procedure or a Python function. Procedures don't have the return statement, functions do in Python. Once defined, subprograms can be called at any point in the main program. You may need to pass values to the subprogram if they have parameters. If you call a function, make sure you have a variable ready to store the value returned. So calling a procedure, doesn't matter if it's OCR reference language or if that is Python, we just use the name and then in brackets, any values that we need to send as parameters to that procedure. So for example, add x, y. If it's a function, we call the function, give it any parameters, but we also have to assign that value to a variable. So here we say answer equals addition, xy, call the addition function, pass it the values stored in X and Y to use, it will return a value that I'm going to store as answer that I can use elsewhere in my main program. Note, read questions about subprograms carefully. If you're asked to write a function, you don't need to create the rest of the main program as well. Just write the function. Equally, if you're asked to call a pre-written procedure or function, you don't actually need to write the procedure or the function. That's already been done. You can assume it's all there and working. Just call it using the appropriate code. Don't create extra work for yourself. Last but not least in this section, we have random number generation. So sometimes you need to generate a random number in the exam. To generate, for example, a random number from 1 to 100, both inclusive, in the OCR reference language, we would say number equals random, and then in brackets 1, 100. In Python, we would say number equals random.randint 1, 100. And that would be a random number from 1 to 100, both inclusive in both OCR and Python. Note, when coding in Python, like real coding, you would have to import the random function first, but don't worry about this in the exam. You're not expected to import library functions. You could just use random.randint. That's fine. Moving on to 2.3, producing robust programs, let's take a look at defensive design. Defensive design involves thinking about problems that could potentially occur and preventing them before they happen. This involves things like anticipating misuse, thinking about the ways the users could cause the program to fail. This could be accidentally or deliberately, but both cases have to be dealt with. You also need to think about authentication. This is the process of establishing a user's identity. This could be through a username and password, possession of an electronic key, device, or account, or biometrics like a fingerprint or a face scan. Input validation is the process of checking data when it is entered to see if it conforms to a rule. This can check that the data entered is sensible, but cannot show that it is correct. 01202343443 is a sensible phone number. Please don't call it, I just made it up at random. But is it the user's real phone number? Now, I'm also going to cover data verification and input sanitization here. They're not technically part of the J277 course. However, when it comes to defensive design considerations, they have been on sample paper mark schemes as possible answers. So data verification is the process of ensuring that the user types in what he or she intends to. For example, making the user enter a phone number or an email address twice to confirm accuracy, or sending a text message or an email to the address given so they can click on it to check that it's real. We also have input sanitization. This checks and modifies any input before passing it on to the next process. For example, changing the case to make sure it's uppercase or lowercase, removing any white space or any special symbols that could crash the program. Maintainability is when the original programmer has deliberately made a program straightforward to understand and modify. To make sure your code is maintainable, you should indent the program structures in the code, add comments to the code that will identify what each section does and how the program is intended to work, use meaningful variable names that will help identify the purpose of each variable, use subprograms to reduce the amount of code and improve efficiency, use whitespace to make the code easier to read. 2.3.2 Testing. The purpose of testing is to ensure the program functions as expected. There's two types. There's iterative, testing during the program development. Each module, each section of code is programmed, tested. You write the next module, you test it, so on and so forth. And you have final or terminal testing. This is testing after the program is finished to make sure all the assembled parts of the program work together in a satisfactory manner. There are different types of error that you might find in your code. Syntax errors are when the rules of the programming language are broken, and logic errors are when the algorithm produces unexpected results. In other words, the program does not do what the programmer intended. Test data should be chosen so the system as a whole can be tested destructively, checking for errors whenever they may occur. Normal, data that is typical input for the system. This should be accepted by the program without causing errors. Boundary. This is data that is of the correct type, but is on the very edge of being valid. Boundary test data should be accepted by the program without causing errors. Invalid. This is of the correct data type, but outside the accepted limits. Invalid test data should be rejected by your program. Erroneous. Data that is of the correct type and should be rejected by the system. For example, if a program expects numeric input, a string would be erroneous input and vice versa. So I'll give you a simple example. It's a program where you have to enter a number from 1 to 10. Normal would be anything from 1 to 10. Let's say 5. 5 is a nice middle acceptable value. Boundary, data that is correct but on the edge of being incorrect. So in our case, the upper boundary would be 10, the lower boundary would be 1. Invalid would be anything less than 1 or greater than 10. So -1 and 15 would be invalid test data. Erroneous would be the letter A or hello or something like that. Refining an algorithm means to improve the code. If testing has picked up any errors, an obvious improvement would be to fix the problems. Other attempts to refine the algorithm may make the code more efficient or maintainable. 2.4 Boolean logic. Boolean logic uses two values, true and false. These are represented in computer systems using binary 1 and 0 values. You need to learn 3 logic gates and their associated truth tables at GCSE level, not, and, or. Here we have an example of a not gate. It's kind of like a triangle with a bit on the end there. I've got not there, and you've also got the symbol there. So it's pretty simple. If you have a look at the truth table, it just reverses the input. 0 becomes 1, 1 becomes 0. Underneath it, we have the AND gate. We've got the conjunction symbol there. Takes two inputs, produces an output. It's an AND, so it only produces a positive, a true response if both of the inputs are also true. Otherwise, in every other case, it outputs a 0. So 0 and 0 gives you 0, 0 and 1 gives you 0, 1 and 0 gives you 0, 1 and 1 gives you 1. It's an AND gate. Then we have the OR gate. Again, I'm giving you the symbol there for disjunction, just in case you see that. Takes two input, produces an output, but this case it returns true if one or either or both of the inputs is true, otherwise it produces a false. If both of the inputs are 0, it will produce 0, but 0 and 1 will give you 1, 1 and 0 will give you 1, and 1 and 1 will give you 1. So it's like the reverse of an AND gate. In the exams, you're going to be expected to know these symbols, be able to draw them correctly. We're not all good artists, guys, but practice a little bit, especially your ands and your ors, to make sure they don't look similar. And you also be expected to know those truth tables, so just memorize them. These 3 logic gates can be combined into more complex logic systems. So here we have not A and B. So given that Boolean expression, not A and B, we have the diagram here. We've got the 2 inputs going into the AND. The output from that, which is R, goes into a NOT gate, and then we have the final output P. And again, we can use that to create a truth table as well. We write down all the possible combinations of the input A and B, and then that gives us the output R and the output P. So it's an AND gate, so 0 and 0 will give us the output of 0. When that goes to the NOT gate, it will get inverted to become a 1. 0 and 1 as inputs A and B will give you a 0. Again, that's inverted to become a 1. 1 and 0 again gives you the output for R of 0, which is reversed, and you get a 1 from the NOT gate. And then finally, 1 and 1 as input will return 1 from an AND. That gives you R of 1. And then the final output there is reversed, and you get a 0. So in the exam, given one of these, the expression, or the logic gate diagram, or the truth table, you should be able to recreate the others, okay? Let's look at another combination. We've got A and B in brackets, or C. So we can draw that. We've got our 2 inputs, A and B, going into the AND gate. We've got a third input, C. The output from the AND gate is R, and R and C both lead into the OR gate, and we've got the final output of P. For our truth table over here, we write down every combination of A, B, and C. It's just a pattern. So that gives us every combination here. You can see A is 4 zeros, 4 ones. B, we get 2 zeros, 2 ones, 2 zeros, 2 ones, and then C is just 0, 1, 0, 1, 0, 1, 0, 1. It's a nice pattern there. You can just use that anytime you have 3 inputs. And then we have to write down what R and P are. So it's an AND. So we know for A and B going into the AND to produce the R, it will only return a 1 if both the inputs are 1s. So mostly going to be zeros. The last 2 rows there are going to be 1s. And then we've got the OR gate, and that has the output of R, which is obviously coming from the AND gate. And then we've got the new input C. So we look at C and we look at R. It's an OR. So that means if one or the other, or both are 1s, it will return 1. Otherwise, it will return 0. So 0 and 0 gives you 0, 1 and 0 gives you 1, 0 and 0 gives you 0, 1 and 0 gives you 1, 0, 0 gives you 0, 1 and 0 gives you 1, 0, 1 gives you 1, 1, 1 gives you 1. Write all that out, and that's your truth table, no problems. And again, given one of these, you should be able to recreate the others. If I give you the expression, you can give me the logic diagram. If I give you the logic diagram, you can do the truth table, etc. Maybe the most difficult part would be applying logical operators and truth tables to solve problems, so problem solving. So an example might be something like this. Imagine a family looking to book a holiday. They have a budget of £2,000 for the holiday, and they would like this to be somewhere with a pool. However, if a holiday in the USA was available at this price, with or without a pool, they would be happy. We can construct this situation as a logic statement. Let P be the outcome of being happy with the holiday. The inputs can also be defined as A, costs £2,000 or less, B, has a pool, C is in the USA. This situation is equivalent to the logic statement P equals A and then in brackets B or C. And the truth table for this logic statement is as follows. So you can work that out. You got A and B and C. B or C, you just write down the truth table for B or C. And then P is whatever the result of B and C is, and A. And you can write all that down. So you end up with a final column of 0, 0, 0, 0, 0, 1, 1, 1. So again, it's just about thinking about it, analyzing it, breaking it down, and then trying to come up with, say, a diagram or a truth table to match that situation. 2.5, Programming Language, Integrated Development Environments, starting with languages. Low-level languages means machine code and assembly language. High-level language, more human-readable like Python, C#, Java, etc. Low-level languages use binary for machine code or mnemonics for assembly language to represent instructions, whereas high-level languages use English-like keywords, print, input, while. Low-level languages are hardware dependent. The instructions are specific to that CPU architecture, whereas high-level languages are hardware independent. The language looks the same and has the same instructions no matter what system it's running on. Translators are used to convert programming code into machine code for the computer to process. There are 3 types of translator. An assembler translates assembly code into machine code. That's only obviously for the low-level assembly code. And then you've got 2 translators available for high-level languages, compilers and interpreters. Compilers translate an entire high-level program into executable machine code, whereas an interpreter translates high-level programs to machine code line by line in real time. Key differences and characteristics of compilers and interpreters. Compilers translate the whole program in one go into machine code and then run it afterwards. Interpreters translate one line into machine code, run it, and then repeat for the next line. Compiler, you will end up with a executable file. So you'll have your source code file, but you'll also have this executable machine code file that will run independently. The interpreter does not produce an executable file. With the compiler, once it's compiled once, the code does not need to be translated again unless you go back and change that original code. Whereas the interpreter needs to be translated every time the program is run. With the compiler, you can distribute the executable so the user does not need to see the source file. With the interpreter, you need to give the user the original source code, and they must have a copy of the interpreter to run the program. Compiled code typically runs very quickly, whereas interpreted code, because it has to be interpreted again each time it's run, tends to be a bit more slow. And finally, the Integrated Development Environment 2.5.2. An IDE, or Integrated Development Environment, is a comprehensive set of tools to develop programs. Common features of an IDE include an editor for writing your code, often optimized for one or more particular languages. Error diagnostics, such as tools for debugging. So it might highlight the mistakes that you've made. Or it might offer step-by-step progression through a program, allowing you to watch the contents of different variables and find out what's happening at a very kind of in-depth level. It'll have a build feature that compiles and links with other needed parts of the program. Version control, so you can have different versions of your program, and if you make a mistake, you can roll back to a previous version. A runtime environment to allow the programmer to run the code and see the output in the IDE itself. And a translator, such as a compiler and possibly an interpreter, depending on the language. It is finished. Everything you could ever possibly want to know about Paper 2, but might have been afraid to ask. It's all there for you. I'm going to go and relax. That was quite a journey. That took a long time to prepare and edit and get everything done. I hope that was useful to you. Hope there weren't too many mistakes. I saw a few typos as I went through that, but nothing too bad. But everyone, best of luck with your studies. Good luck in all your tests. I will see you next time.